Okay. So the next concept which we are studying is degrees of freedom. So listen, what is meant by degrees of freedom? So a molecule can travel in how many methods, in how many ways, which are independent of each other. That number of ways in which a molecule can travel is called as degree of freedom. Are you able to understand? So movement can be of two types, no? Body can move in a straight line, molecule can move in a straight line, and molecule can rotate also. So two types of motions are there. Either it can move in a straight line or it can rotate about any axis. So these are the two types of motions which we have. Now we will study about each type of molecule independently, and we will try to study how many types of degrees of freedoms are possible. Clear, Nama? So first of all, I will take monoatomic molecule. Monoatomic molecule. What is meant by monoatomic molecule, ma? In this molecule, there is only one atom. Okay? Helium, argon, neon, xenon, krypton, all these are inert gases, no? So they doesn't react with another gas. Okay? So they have only one atom in their molecule. Okay? So for example, if I take this single molecule, okay, ma, and if I study its translational motion, see, ma, this molecule, it can travel along x-axis, no? If I supply some energy to this one, it can travel along x-axis. So it has 1 degree of freedom along x-axis. It has the freedom to travel along x-axis, no? So it has 1 degree of freedom. Same molecule at the same time, it can travel along y-axis also. Clear, no? In two-dimensional motion we have studied, no? Body can simultaneously travel along x-axis as well as along y-axis. So it can travel along y-axis also. Similarly, same molecule, it can travel along z-axis also simultaneously. Are you able to understand, ma? It can travel out of the board, it can travel inside the board also. So therefore, this monoatomic molecule, it has 3 degrees of translational freedom. Translational means moving in a straight line. So how many degrees of translational freedom? 3 degrees of translational freedom is present. Okay. And this molecule, it can rotate also. This molecule can be rotating also. No? But for ideal gases, what we consider for ideal gases, the size of the molecules is very less. Okay, ma? What is the formula for rotational kinetic energy? Rotational kinetic energy is half I omega square. This is the equation for rotational kinetic energy, no, ma? Translational kinetic energy, half m v square. But rotational kinetic energy is half I omega square. What is the moment of inertia? Moment of inertia for a sphere, solid sphere, you can write it is 2 by 5 mr square. Are you able to understand? But their radius is very, very, very small, no? Because we are taking gases to be ideal gases, their moment of inertia will be almost 0. Okay, so therefore you need not consider their rotational kinetic energies. Are you able to understand, ma? Because they are point masses, their moment of inertia will be very small. Okay, so therefore for monoatomic molecules we take only translational motion. Rotational motion is neglected. Are you able to understand? So right now. So therefore we say this molecule can travel, okay, ma, along x-axis, y-axis, z-axis. Okay, ma? Therefore, it has 3 degrees of translational motion. 3 degrees of translational freedom. Okay, ma? It has 3 degrees of translational freedom. Are you able to understand? Because molecule is very small, clear, ma? Its rotational motion is neglected. What we do to its rotational motion, ma? We neglect its rotational motion. Are you able to understand? So therefore, totally how many degrees of freedom it has? Only it has 3 degrees of freedom, and that too which kind of freedom? Only translational freedom. Understood, Nama? Therefore, total degrees of freedom is degrees of freedom due to translation, degrees of freedom due to rotation. So it is 3 plus 0, so totally 3. So therefore, degrees of freedom of monoatomic molecule is how much, ma? It is equal to 3. Understood, no? So we consider only degrees of freedom in translational motion. In rotational motion, its degrees of freedom is neglected. Understood, Nama? Now if I take a diatomic molecule. Okay, ma? So what is meant by diatomic molecule, ma? Diatomic molecule means it has only 2 atoms. Clear, no? In its molecule, it has only 2 atoms. So these are the 2 atoms. Are you able to understand? And they may be connected by some bond. Okay? Bond is not a physical thing, it is a force of attraction. Okay? So they are connected by some bond. Let us consider like this. Now see, this total molecule, it can move along x-axis, no? This total molecule, it can move along y-axis. So this total molecule can move along z-axis also. So how many degrees of translational freedom? 3 degrees of translational freedom. So I write 3 degrees of translational freedom. Okay. So I write Ft is equal to how many? Ft is equal to 3. Understood, Nama? Similarly, if I study their rotational motion, let us see. Okay. Same molecule I will take. Okay, ma? We take the same molecule. Okay. Now see, this molecule, it can rotate along how many axes? See, this is an x-axis. Okay. Around this x-axis, molecules can rotate, no? Then we should not neglect their rotational kinetic energy. Why? Because molecules are rotating around an axis, and axis has a particular distance. There will be bond length, no? Bond length is not very small. It is comparatively bigger only. Clear? So therefore, this total molecule, now this is y-axis, no? They can rotate along y-axis. Understood? So 1 degree of rotational freedom. Okay. Same molecule can rotate along z-axis also, no? Z-axis will be like this. Okay. So if axis is like this, molecules can rotate like this. Okay, ma? So therefore, 1 degree of freedom along z-axis also. But if you take the rotation along x-axis, then this can be neglected. Okay, ma? Rotation along x-axis can be neglected. Why? Because axis is passing through the molecules, no, ma? X-axis is passing through the molecules. And molecules are considered very small, no? So you can neglect their rotational kinetic energy. Are you able to understand? You cannot neglect the rotational kinetic energy when axis is passing along y-axis. You cannot neglect the rotational kinetic energy when axis is passing through z-axis. But you can neglect the rotational kinetic energy when axis is passing through the molecules itself. Okay. So therefore, here also how many degrees of freedom? 3 are there. But 1 degree of freedom we are neglecting. So totally how many degrees of freedom? 2 degrees of freedom. Are you able to understand what is happening? So make note of this point. So what we write for diatomic molecule, okay, we neglect that motion which is whose axis is passing through both molecules. Okay, ma? So that degree of freedom we will neglect. Are you able to understand? So therefore, how many degrees of freedom, how many degrees of rotational freedom we take, ma? 2 degrees of rotational freedom we will consider. So therefore, totally how many degrees of freedom it has? So F translational plus F rotational. Okay, ma? So totally 3 plus 2 is equals to 5 degrees of freedom a diatomic molecule will have. Are you able to understand? Diatomic molecule will have 5 degrees of freedom. Understood, no? Similarly, now we will consider about triatomic molecule. Completed, ma? Okay. So, triatomic molecule. So, what is meant by triatomic molecule? In triatomic also we have 2 types of molecules, ma. We have 2 types of triatomic molecules. What are they? Okay, ma. First one is linear triatomic. So linear triatomic molecule, and the second one is non-linear triatomic molecule. Okay. Linear triatomic molecule means what? Linear triatomic molecule means marker advetnare. Okay. Linear triatomic means all the three molecules, they are in a straight line. Okay, ma? This is called as a linear triatomic molecule. Okay, ma? So all the three molecules, they will be in a straight line. Okay. If molecules are present in a straight line, then can you say how many degrees of freedom it can have? Totally, how many degrees of freedom? This will have 5 degrees of freedom. Why? Okay, ma? 3 translational degrees of freedom. They can move along x-axis, they can move along y-axis, they can move along z-axis. But they will have only 2 degrees of rotational freedom. And if axis is passing like this is axis. Okay, ma? Then this moment of inertia can be neglected, no? This moment of inertia or this rotational kinetic energy can be neglected. So therefore it has only 2 degrees of rotational freedom. So totally how many degrees it has? So total degrees of freedom is F translational plus F rotational. Translational degrees of freedom 3. Okay, ma? Rotational degrees of freedom 2. So totally 5 degrees of freedom. Are you able to understand? If it is a linear molecule, all molecules arranged in a straight line, if axis is passing along all the molecules, that moment of inertia can be neglected. Okay, so therefore rotational kinetic energy also can be neglected. Now what about a linear, non-linear triatomic molecule? Non-linear means what? So consider this is one molecule, here there is one more molecule, and consider here there is one more molecule. Okay, ma? Now how many degrees of translational freedom?
6.
Translational freedom. 3 degrees of translational freedom, no? All these set of molecules, 3 molecules, all of them they can move along x-axis. All of them they can move along y-axis. All of them they can move along z-axis also. So therefore definitely I can say translational freedom is equal to 3. Actually translational freedom will be always 3, ma. Whether it is monoatomic, diatomic or triatomic, this is always present. Always molecules can travel along x-axis, y-axis and z-axis. Clear, no, ma? Now coming to rotational freedom. Okay, ma? So consider axis is passing like this along x-axis. Okay. You can neglect moment of inertia of this one and you can neglect moment of inertia of this one. But moment of inertia of this one cannot be neglected, no? Are you able to understand, no? If axis is passing like this, molecules are rotating like this. That is the meaning of this one, no? Definitely you can neglect moment of inertia of this one and this one. But what about this one? This is at a very large distance from axis, no? If molecule is present at a larger distance, moment of inertia increases. Moment of inertia depends on 2 factors. Already we studied, no? It depends on mass also, distribution of mass also. So mass is present at a larger distance. So you cannot neglect its moment of inertia. Okay. Similarly, if axis is passing like this, now molecules will rotate how? This is how molecules will rotate. Clear, no? You can neglect moment of inertia of this one, but you cannot neglect moment of inertia of these 2. Understood, no? Similarly, when axis is passing like this, perpendicular to the board or out of the board or inside the board, then you have to consider moment of inertia of all the 3 molecules. It means in a non-linear triatomic molecule, you have to consider all the 3 degrees of rotational freedom also. You cannot neglect anyone here. Are you able to understand? So therefore, how many degrees of rotational freedom? So rotational freedom is equal to 3. So therefore, totally how many degrees of freedom? F is equal to 6. 6 degrees of freedom it will have. Understood, no? So this is how we can calculate the number of degrees of freedom for monoatomic, diatomic and triatomic molecules. Understood, no, ma? Yes, make a note up to here. Okay, ma? So the next concept which we are studying is law of equipartition of energy. Clear, ma? It says that, so write down first of all, we will write the statement of this one. Okay, ma? So every degree of freedom will have same energy, okay, ma? And it is equal to half kT. Okay, ma? This is called as law of equipartition of energy. Okay. Equipartition means what? Dividing equally, no? Dividing equally. So monoatomic molecule will have how many degrees of freedom? 3. So every degree of freedom will have how much energy? Half kT of energy. Are you able to understand? So Motion along x-axis, same energy. Motion along y-axis, same energy. Motion along z-axis also, same energy. Okay. Similarly, if you take a diatomic molecule, 5 degrees of freedom. What are the 5 degrees of freedom? 3 degrees along translational, 2 degrees along rotational. And every degree of freedom will have how much energy? Half kT of energy. So like this energy is distributed. Are you able to understand, ma? So that division of energy equally, that is called as law of equipartition of energy. Okay, ma? So therefore, for example, if you take a monoatomic molecule, okay, ma? If you take a monoatomic molecule, so totally how many degrees of freedom it has? Or we can do one thing for monoatomic molecule, total energy. Okay, ma? Total energy of monoatomic molecule, how can I calculate? How many degrees of freedom totally? 3 degrees of freedom. Each degree of freedom will have how much energy? Half kT of energy. So therefore, what is the total energy of a monoatomic molecule? It is 3 by 2 kT. This derivation already we have done. Do you remember? Each molecule will have 3 by 2 kT of energy if it is an ideal gas molecule. And monoatomic molecules, they behave like what you call ideal gases when temperatures are very high and pressures are very low. Are you able to understand, ma? So therefore, total energy of monoatomic molecule is number of degrees of freedom multiplied by energy possessed by each degree of freedom. That is how you have to write. Or you can write like this. Just you can write F multiplied by half kT. Understood now? F multiplied by half kT. Each degree of freedom will have half kT energy. Equal distribution is there, no? And how many degrees of freedom? 3 degrees of freedom. So total energy F into half kT. Clear now? Similarly, if I write for 1 mole of molecules, 1 mole of monoatomic molecules, then how I have to write? Into Avogadro number, that's it. So I will write F multiplied by half kT. This is the energy possessed by each molecule, no? Single molecule. Now 1 mole means I have to multiply with how many number of molecules? Na number of molecules, Avogadro number of molecules. And K into Na? R. Already we studied, no? K into Na is called as R. So therefore, how I have to write? I have to write F multiplied by half RT. Okay, ma? So this is the total energy possessed by 1 mole of molecules, monoatomic molecules. Okay, ma? So F value is how much? F value for monoatomic? For monoatomic, F value is 3. So therefore, energy possessed by 1 mole of monoatomic molecules, 1 mole of monoatomic molecules is how much, ma? It is equals to 3 multiplied by half RT. Or you can write 3 by 2 RT. You can write like this. Understood, no? Similarly for diatomic, F into half RT. So 5 by 2 RT. For triatomic, 6 by 2 RT, 3 RT. Understood, no? Like this you can write. So write down. Okay. So therefore we write total energy of diatomic molecules. Again same formula. F multiplied by, for 1 mole, ma, this you should not forget, for 1 mole. For a single molecule you have to write a K, ma. For mole of molecules you have to write R. That's it. So F into half RT for 1 mole of molecules. So number of degrees of freedom? 5. 5 into half RT. So it is 5 by 2 RT. Clear? Similarly, total energy of linear triatomic mole of molecules. For this one, for linear triatomic, how many degrees of freedom? 5 only. Linear triatomic, 5 degrees of freedom. So F into half RT. F value 5. 5 by 2 RT. That's all. No? For non-linear triatomic, 6 degrees of freedom. 6 by 2 RT is 3 RT. Like this you can calculate. Okay, ma? So therefore, total energy of non-linear triatomic molecules is how much? It is F into half RT. Okay, ma? This is also for 1 mole of molecules. So 6 by 2 RT, which is equals to 3 RT. Understood, ma? Now if you want to calculate energy for 2 moles, 2 into total energy, 2 into 3 RT. Are you able to understand? For n number of moles, n into 3 RT, like this. This is the calculation for 1 mole, no? 2 moles means you have to multiply by 2. 10 moles means you have to multiply by 10. That's it. Okay? So therefore, let us write that also. Okay, ma? So, energy of 1 mole of molecules is how much? It is number of degrees of freedom multiplied by half RT. That's all, no? So energy of n moles of molecules. Okay, so it is n into F into half RT. Clear, no? And F can be anything. F can be 3 also, F can be 5 also, F can be 6 also, depending on the type of molecules which we are using. Okay, so this is a very important equation. Okay, so F can be 3 also if it is what kind of molecule? Monoatomic molecule. Okay, F can be 5, it can be diatomic also, and it can be linear triatomic also. That's all, no? And F is equal to 6, it can be triatomic non-linear molecule. So these are the different conditions which you are supposed to remember. Fine? Okay, Sima. So this is the next question. So calculate the number of degrees of freedom of molecules in hydrogen, 1 cubic centimeter of hydrogen at normal temperature and pressure. Okay, ma? So how much volume of hydrogen he is giving? Cc. Cc means cubic centimeter, no? It means it is a volume. 1 centimeter length, 1 centimeter width, and 1 centimeter height. So in that cube, how many molecules of hydrogen will be present? First of all, I have to calculate that thing. Are you able to understand? Sima. So at NTP, normal temperature and pressure, 1 mole of any gas, 1 mole of any gas will occupy how much volume? 1 mole of any gas will occupy 22.4 liters. This you should have studied previously, no? In chemistry also you should have studied, no? At normal temperature and pressure, 1 mole of any gas, whether it is oxygen gas, hydrogen gas, helium gas, whatever it may be, it will occupy how much volume? It will occupy 22.4 liters of volume. Understood, no? So therefore, this is the volume given. In this volume, 1 mole of molecules will be present. So 22.4 liters, I can also write it as 22.4 multiplied by 1000 milliliters. I can write like this also, no? Milli means 10 power minus 3, no ma? Milli means 10 power minus 3. 1 liter is equal to how many ml? 1000 ml, 1000 milliliter. And 1 ml is called as, 1 ml is nothing but 1 cc. Ml and cc both are same. Milliliter, cubic centimeter, both are same. Clear, no ma? Therefore, 22.4 liters can also be called as, can I write it as, okay, I will write like this only, 22.4 into 10 power 3 cc. Are you able to understand, ma? So in this volume, how many molecules will be present? So in this one, 6.023 into 10 power 23 molecules of hydrogen will be present. That's all, no, ma? That is the meaning of this one, no? 1 mole of gas will occupy this much volume. And 22.4 liters can also be written as 22.4 into 10 power 3 cc. So in this volume, this many molecules will be present, no? So therefore, how many molecules will be present in 1 cc? Therefore, number of molecules in 1 cc. 1 cubic centimeter will be how much? So just to say, send this total value to the other side. Therefore, the answer is 6.023 multiplied by 10 power 23 divided by 22.4 multiplied by 10 power 3. Then I will get the number of molecules which are present in 1 cc. Are you able to understand? And let us see what is the value he gave. It is 2.688 into 10 power 19. Okay, ma? So 2.688 into 10 power 19. So these many molecules will be present in 1 cc of volume. If I take a small, when cc means very small, no, this much volume. So in this much volume, these many number of hydrogen molecules will be present. Are you able to understand, ma? So H2 molecules in 1 cc. Are you able to understand? And H2 molecule, is it a diatomic molecule, monoatomic or triatomic? Diatomic molecule. Each diatomic molecule will have how many degrees of freedom? 5 degrees of freedom. How many molecules are there? These many molecules are there. So total how many degrees of freedom? Therefore, total degrees of freedom is equal to how much? 5 multiplied by 2.688 multiplied by 10 power 19. If you do this total calculation, then I will get the total degrees of freedom present in 1 cc of volume of hydrogen. Understood, no? ఇది ఆన్సర్. మీరు 3, 10, 14 అంటే గుండెపోటు ట్రాకింగ్ ఏం వస్తుందిరా? కమాన్. క్వశ్చన్ ఏం అడిగినాడు మరి? ఒక మాలిక్యూల్కి చెప్తే ఎట్లా మీరు? So therefore the answer is 1.344 multiplied by 10 power 20. So this is the total degrees of freedom present in this 1 cc of container. Okay, ma? Sima, if it is oxygen gas, same. If it is helium gas, molecules are same. Molecules remain to be same, but instead of 5 I have to write 3 because helium is a monoatomic gas. Are you able to understand? Like this. So just for any gas occupy same volume, no ma? That is Avogadro's law, no? A fixed volume of any gas, when it is maintained at same temperature and pressure, okay ma, they should have same number of molecules. Okay, that's it. Okay ma. See this question. So calculate average kinetic energy of translation of an oxygen molecule. It means he is asking about single oxygen molecule at 27 degrees Celsius. Okay, ma? And he is asking which energy? Only translational energy. It means energy in a straight line. So how many degrees of freedom are present in traveling in a straight line? 3 degrees of translational freedom is there, no? So therefore answer for first one is number of degrees of freedom multiplied by half kT. That's all, no, ma? Because he is asking about single molecule. Okay. And also which degrees of freedom? Only Ft only he is asking. Degrees of freedom in translational motion. How many degrees are there? 3. So 3 multiplied by half kT. Okay, ma? And if you want to substitute K value and T value, you can substitute. So 3 by 2 multiplied by K value is how much, ma? K value is 1.38 into 10 power minus 23 multiplied by temperature he given Celsius, no? So 273 plus 27. If you do this calculation, you will get the total energy of only translational motion. That's all, no? Similarly, total kinetic energy means rotational as well as translational, both we have to consider. That's all, no? So therefore, for second one, so total energy is equal to, it is nothing but F into half kT. Okay, ma? But oxygen is a diatomic molecule, so number of degrees of freedom will be 5. So 5 into half kT. And substitute K value and T value, then you will get the next answer. Clear, no? Similarly, option C, question C. So total kinetic energy in joules for 1 mole of molecules. 1 mole means? So total energy for 1 mole of molecules means, so again number of degrees of freedom multiplied by half RT. This is what we have to write, no? Half RT is the energy possessed by mole of molecules. Half kT is the energy possessed by one single molecule. That is the difference, no? So just substitute. How many degrees of freedom? 5. Half R value 8.31 multiplied by temperature is 273 plus 27. So do this calculation, you will get answer in joules only. Because R value is SI system, no ma? 8.31, that is in SI system. Okay? That's it. So just Answers I will not say. You calculate yourself. Okay? Student. So gaseous mixture consists of 2 moles of oxygen and 4 moles of neon at temperature of T. Okay, ma? Neglect all vibrational nodes. It means vibration we are neglecting, we are taking only translation and rotation. Okay? Then calculate the total internal energy of the system. Internal energy is nothing but kinetic energy only, ma. Clear? So therefore, because vibrational energy comes also under energy, but he is asking us to find out, neglect it, no? Internal energy is of many types. Kinetic energy is also internal energy. Rotational energy also internal energy. Vibrational energy is also internal energy. Potential energy is also internal energy. We are neglecting remaining energies. We are taking only translational energy and rotational energies as internal energy. So therefore, total internal energy of the system is equals to, so first of all, oxygen. How many moles of oxygen? 2 into F into half RT. This is how I can write now. For 1 mole of any gas, half RT is the energy number. And how many degrees of freedom? F. And how many moles? 2 moles. This is how I have to write now. So therefore, 2 into, how many degrees of freedom are there for oxygen? Oxygen is a diatomic gas, no? So therefore, 5 degrees of freedom multiplied by half RT. Okay, ma? So 1 by 2 gets cancelled. So it is 5 RT. 1 minute. Okay, ma? So, and for oxygen also we have to calculate, no, ma? Oxygen already we have calculated, no? We have to calculate for what we call neon also. For neon, what is the total energy, ma? How many moles initially? 4. So degrees of freedom multiplied by half RT. That's all, no? So 4 into, neon is what kind of gas? Monoatomic gas. It is an inert gas, no? Only one atom will be present. So 3 degrees of freedom will be 3 multiplied by half RT. Okay, ma? So 2 ones are 2 2s are, so therefore it is 6 RT. So therefore total internal energy is how much? Total internal energy is equals to 5 RT plus 6 RT, which is equals to 11 RT. So this is the total internal energy of this gas. Clear? That's all. See this question, ma? So light container, it means you are not supposed to calculate the mass of this container, ma? This is a container. A light container having a diatomic gas enclosed within is moving with the velocity of v. It means this total lorry, it is moving with the velocity of v. So mass of the gas is capital M, okay? And the number of moles is N, okay? Total mass of the gas is how much? Mass of gas is capital M, okay, ma? And the number of moles are N. Then the first question is, what is the kinetic energy of gas with respect to container? What is meant by with respect to container? It means there is an observer inside the container. That is the meaning of this one, no, ma? Observer is present inside the container and he is observing the molecules of this gas. Are you able to understand? So because we are solving with respect to container, observer is container, no? And observer always goes into rest position, no? So it means that we have to neglect the motion of this container, because relatively observer will be in rest position, no, ma? So to this observer, what he will observe? He will observe only velocity of the gas molecules, their natural velocity, velocity with which they are moving inside the container. That only he will observe. So therefore answer for the first one is kinetic energy of gas, okay, ma, with respect to container itself is equals to, just you can calculate its internal energy. So number of degrees of freedom multiplied by half RT. This is the equation, no? This is what kind of gas? Diatomic gas. So number of degrees of freedom? 5 multiplied by half RT. That's all, no? How many number of moles? N number of moles is there. So multiplied by N. So N into, okay, ma? So N into 5 into half RT. Okay, ma? Or you can write 5N by 2 RT. Okay, ma? So this is the total energy of the container, or total energy of the gas with respect to the observer present inside the container. Are you able to understand, ma? Okay. Now he is asking second question. What is the second question? Kinetic energy with respect to ground is how much? Kinetic energy of same gas molecules with respect to ground is how much? What is meant by with respect to ground? So on the ground there is an observer, okay, ma? And he is observing these gas molecules. Then to this observer he will observe two velocities. One is velocity of the molecules inside the container, and second one is motion of total molecules towards right side direction. That velocity is also there. No? Are you able to understand? Ma? This observer will observe two velocities. What are they? One velocity is the random motion of molecules, which is called as internal energy, this energy. One more is total container is moving in this direction. No? So that kinetic energy also will be observed by this person. Whereas the observer inside the container, he cannot see the motion of the total container. Vaadiki container motion kanpinsadu kada, because he is present inside the container. Are you able to understand? Ma? Therefore, what we say, observer on the ground, okay, ma, will see two motions. What is the first motion? Random motion of molecules. Random motion of molecules of gas, and motion of container also. Motion of container. Both he will see, no? Therefore, for this person, kinetic energy will change. So what is the total energy in this condition? Random motion already we have calculated, no? 5 by 2 nRT. So that is 5 by 2 nRT plus, and in addition to this one, he will see kinetic energy of this gas also, no? What is the formula for kinetic energy? Half mv square. What is the total mass of the gas? M. And velocity is v. So therefore, additional energy is half capital M into v square. That's it. Are you able to understand how we are solving? That's it. Right down. So there is an insulated container containing monoatomic gas of molar mass M. It is moving with a velocity of v naught. Okay. So therefore, consider this is a container. And how many moles of gas is present, that we don't know. So let us consider n moles of gas is present. Okay, ma? And molar mass is given as M. That is capital M he gave. It is equal to small m. Are you able to understand, ma? Now this total container is moving with how much velocity? It is moving with a velocity of v naught. So if container is suddenly stopped, are you able to understand? Then find the change in temperature of the gas. Okay, ma? So initially when container was moving, how much total energy the gas molecules will have, ma? Total energy will be equal to, first of all, it is what kind of gas? Monoatomic gas, no, ma? So number of degrees of freedom multiplied by half RT, and if I consider n moles of gas, I have to multiply by n. That's all, no? So for monoatomic gas, F value is 3. So F into half RT is the energy possessed by each degree of freedom. And how many moles of gas are there? N moles of the gas are there. He didn't give, we have assumed n moles of gas to be present. And in addition to that one, if number of moles are n, and molar mass is small m multiplied by v squared. This energy is also there, no? All the molecules, they are moving with some kinetic energy also, no? Ma? So in addition to internal energy, the gas molecules, they have kinetic energy also. Velocity he gave v naught square, no? So half m v naught square. What is small m? Mass of 1 mole of gas. Molar mass he has taken as small m. How many moles of gas are there? N moles. So total mass is n into m. That's all, no? So this is the total energy possessed by the gas when gas is moving. Are you able to understand? Now what happens is, when this container suddenly stops, when container we are applying brakes to the gas suddenly, then what happens? Sima. So energy should be converted into some another form of energy, no? According to law of conservation of energy, energy cannot be created, energy cannot be destroyed. It has to be converted from one form to another form. Are you able to understand? So therefore, this total kinetic energy suddenly becomes 0. When I stop the container, kinetic energy will become 0, no? Molecules motion will not stop. But motion of molecules in straight line, that will stop. And that remaining energy should be converted into some another energy. And what can be that energy? That energy is nothing but change in internal energy. Are you able to understand, ma? So write down. So therefore what we write, as container stops, clear, ma? The kinetic energy of molecules again convert into internal energy itself. Okay, ma? Therefore velocity further increases, velocity of molecules with respect to container. Velocity of molecules with respect to container further increases. So temperature also changes, or you can say temperature also increases. If velocity of gas molecules increases, temperature also definitely increases because temperature depends only on kinetic energy. Already we discussed, temperature depends on what? Only kinetic energy. So when velocity of molecules further increase, then temperature also increases. So therefore, how can I calculate a change in temperature? Let us see. Okay, ma? So change in temperature. So which energy is converting into additional internal energy, ma? This energy. This energy is disappearing, no? So that energy will again convert into internal energy of the gas molecules itself. Okay. So therefore, half Nm multiplied by V0 square. This is equal to change in internal energy. This converts into what? Change in internal energy. Okay, ma? And what is the internal energy possessed initially? So number of degrees of freedom are N, number of moles are F, N, and half R. Instead of T, I have to write delta T. Why I am writing delta T, ma? Because I want change in temperature. T is total initial temperature. Okay, ma? But when container suddenly stops, the total kinetic energy is converted into, again, internal energy of the gas molecules. So temperature will rise. Temperature will increase because each molecule will now have greater velocity in random motion. Okay. So therefore, instead of temperature, I have to write this is the change in temperature because of this additional energy obtained by the gas molecules in the form of internal energy. Understood? No? So therefore, change in temperature is how much? So what are there any terms which we can cancel, ma? So number of moles we can cancel, and still there is nothing. Half and half also get cancelled. So still, so m V0 square divided by F into R. That's all, no? Correct only, no? M V0 square divided by, here F is present, R is present, F into R. So this will be the change in temperature. Understood, Nama? This energy will be present. This energy, it is always present. Okay? But temperature changes by this much of amount. Temperature increases by that much amount of value. Clear? That's it.